Our next invited talk is by Jason Corso from Buffalo. He'll be talking about a variety of things.
Yes,
including but not limited to their entry into the context.
I can say that in 30 seconds. We ran Action Bank from UC at 50. We didn't have the time to really invest in the competition. I do apologize for that. But I'll talk about some other things, or some related things, including quotes, actually. So, I'm glad to be here. Thanks very much. So, in the spirit of the workshop, this talk will be about what doesn't work, or what didn't work for us, actually. I think that will be useful. And POSE is included in there. Although if you do use POSE with action recognition like that trajectory, you do see a 3% or so improvement like Cordelia said. But, so that'll take up maybe half the talk, maybe a third of the talk. Then I'll supplement it with what I think has a lot of promise, which is sort of the shape of the action or segmentation. And we've carried out a human psychophysics study on some segmentation videos that show there's quite a bit of information about not only the action but also the actor in the material. Okay, so the first part is about pose and motion, and if I can begin by just kind of asking you a little bit some questions, right? So you all know the UCF 50 classes. What action is this? Drumming? Diving? Swimming? Biking? Bench press? Shooting baskets? Baseball pitches? Yeah, so that was pretty easy, right? These are just 2D frames. These are not special. I went to my hard drive, ran a script to take a random video from each class and a random frame. You guys got, I think it's 7 out of 8 correct. Okay, and the one that's wrong is not that it was wrong, it's just not specific enough. And we'll see here, right? So you did it even when the diver is barely visible due to JPEG encoding, or multiple JPEG encoding. Right, and this here is not swimming, it's actually breaststroke, which is a type of swimming. Okay, but that's a minute detail. Okay, so the first two things I want to talk about are based on observations like this that my students and I made. We tried some things that the action recognition community wasn't really doing. And basically, they didn't work. So there's something to motion. Right? There's a reason why that trajectory is working well. But I can't tell you exactly what that is yet. Okay? So we'll talk about pose-based action classification, the way we did it. And then a variant of Action Bank called actionbank.2D, which just uses image templates instead of 3D templates. With hog descriptors and even off descriptors. And then after that, I'll be talking about a new direction that my group is taking, which uses video over segmentation with super voxels as a low-level representation. And then we have some results that are quite promising about that. Okay. I'm pretty sure most of you probably saw this video from Johansson. This is a famous video from the psychology literature, right? That was sort of a little bit really stop. No one can deny that you can describe in quite rich language what's happening with these 7 or 8 dots. Climbing stairs, moving, sitting, but until there was motion of those dots. Right? If you're following in the middle, there's a guy sitting down, you kind of translate it backwards, you didn't get much there. Okay, so we wanted to play with human pose or action recognition. Okay, there's been quite a bit of advances in skeletal pose estimation in the last 4 or 5 years. For example, the Young-Grumman method can do human pose estimation in pretty drastic poses, like the guy shooting the basketball thing. And did a pretty good job. Okay, but if you look at the distribution of skeletal limb extreme up for various actions, and this is just KTH actions like boxing, hand clapping, hand waving, jogging, and so on. There's quite a bit of overlap. For example, all of the leg, left foot, and right foot locations are essentially the same for most of the actions in these 6 actions here. Okay, the left hand varies depending on if it's hand waving or jogging and so on, but in some sense there's quite a bit of overlap here. Okay, so moving beyond static pose, we developed a detector or a representation called dynamic pose, which essentially is an approximation of temporal pose trajectory over the video. Right? So if you run the Young and Raman pose detector on typical videos from YouTube, they're very noisy. I'll have some results later on. So you can't really trust this as a true carving out of the pose through space-time. Okay, so rather than directly using this 3D or space-time pose, instead dynamic pose takes a first-order Taylor expansion of that pose trajectory, and at each joint point, just describes that skeletal joint point with a Hog 3D descriptor. So it's kind of like describing the direction that that pose skeletal joint point is moving in, right? So in this case, in here you see the girl's arms are moving out when she's kind of separating this way, and then moving in when she's retracting. So these two, although skeletally they're the same, the dynamics are different. So we wanted to incorporate the motion into the skeletal pose. Okay, we ultimately really use sort of a bag of pose representation, so we had to have a way of creating distance between these dynamic poses, and it's very simple. So H's here are the histograms at each joint point P and Q. So P and Q are two poses, joint points are I, and so essentially if the skeletal joint is too far, farther than some threshold gamma, we'll just use a constant penalty for the distance of that point. If indeed they're close enough as a function of gamma, then we'll actually take a distance of their Hog 3D histograms to modulate that actual joint distance there. Okay, you can kind of see again this is just a picture for this guy doing his pressing. When he goes up, we want a different pose when he's going down. Okay. You can actually see that popping out. So these are actual dynamic pose codebook entries on the KTH data set, where you see the first guy here looks a lot like the second to last one over here. But if you actually back project that back into the video, you can see that the first one here is for one of the guys doing the upward motion of the jumping jack, and this guy here is when he's doing the downward motion of the jumping jack. Again, this will ultimately turn out to give you about a 10% improvement in action classification. Okay, but that's not going to matter too much because the overall classification is going to be pretty poor. Okay, so we use a bag of pose type approach. Nothing special here. We're not playing with like Fisher encoding and various RBF kernels and all that stuff. We just want to get a sense for whether or not these things are going to work. Okay, so how do they compare? On small data sets first. Okay, so vertical axis here is the overall accuracy of the method. Okay, the horizontal axis is sort of twofold. These are the sort of sixth class, ninth class, but also the right progression is actually in time. So these are papers published in roughly 2004, 2006, 2007, all the way through, I think this graph goes to about 2012. Okay. Skeletal pose is about 8 years back. Okay. Raw skeletal pose. And this is state-of-the-art skeletal pose. This is not not a format. This is the best that our community can do right now. Okay. Dynamic pose. Okay, it's a little bit better. Actually, significantly better, but still also significantly worse than basic low-level feature methods. Okay. And this message gets even worse when you start talking about larger class performance, like UCF50. And this is also compounded by the fact that in UCF50, as was brought up by Cordelia, in many cases, not the whole human body is visible. In some actions, multiple humans are visible. And so we're just taking a bag of pose over the whole video. Okay, so this is a problem. So you have to actually combine it with some low-level methods. And although I don't have the results on these slides, if you do that, for example, if you do take like action bank plus dynamic pose, you'll get to improve this by about 4%. So there is some complementarity between directly focusing on pose and focusing on low-level features or mid-level features. Okay, I think the main reason why this is the case is that pose is simply noisy. These are just frame-to-frame Young and Ramanan results on UCF50 for cases in which the full human is visible. Okay. And you just see, even in the case with the backgrounds, the pretty simple background, drastic difference here. The pose is very noisy. Again, static background, but large motion. Here's static background and not a lot of motion at all. Look at how the hips are moving.
So this is all UCF50 or this is videos of UCF50?
All of UCF50. Yes, and I don't have them on my website, but we reviewed them. It's a bit of a burden, so if you want them, just send me an email. It's about 60 meg of data. Yeah, so I'm happy to share them. We just sent them to, I think, Juan Carlos the other day.
Could we also also do some more because they do very interesting.
To avoid that, we compute just Hog 3D in the video volume. around the joint points because we didn't want to get into the whole notion of smoothing or pump filtering and so on. Yeah, but I think the right thing to do, if you wanted to use pose, sort of like this more version 2, would do some sort of filtering over the pose to get a better pose estimate in the video.
So the pose is computed just using single frame.
Single frame. Yeah, and
The
there's some
top
more.
3D point will still be translated to the wrong position in some frame, right? That's basically what.
It is, yes, it will be, yes. Okay, so that's the pose story, if you will. And then, I'm sure most of you are familiar with Action Bank, but the basic idea with Action Bank is to create this action space that's spanned by a set of canonical or exemplar actions. Okay, in this case, these are all from music, I believe, like spinning the discus and golfing and horseback riding and so on. The way it worked in Action Bank is that we had 3D templates for each of these that were manually selected, but some are arbitrarily selected from the video volumes. And then we do an embedding into a motion space by Corso's work called action spotting. Ultimately, get a set of 3D correlation volumes, turn those into feature vectors by volumetric max pooling, and run through sparse SPMs here. On smaller data sets, this was the first method to sort of close or win those data sets. But on larger data sets, the method hasn't matured as well as we would have hoped initially. I guess this might be because the actual templates are crucial and they're not automatically selected in Action Bank. And there's some results from the first paper that show if you increase the number of templates in your bank, you'll get increasing performance. And for example, on UCF 101, we did not add UCF 101 bank entries. Now that we have some more time, we plan to do that now and see where we get. But anyway, so as I said, Action Bank is based on these 3D space-time oriented energies. Essentially decompose this video into a set of 7 motion directions, like leftward motion, rightward motion, and so on. Here you have static, and this is sort of just lack of structure here. In our work, we remove the static energy and the lack of structure from these motion volumes. You kind of get a focus on the moving human as a representation in 3D. Okay, but based on the slides I showed you, those 10 image examples in the beginning, we want to see, can we exploit just this scene structure, basic scene and image understanding as a way of modeling action in this data set, in UCF 101 or UCF 15. Okay, so what we did was just essentially extract 2D templates by doing simple k-means clustering on hog features that were run over the videos, every frame separately. Okay, so we automatically selected the templates in this place, and then just use the standard Action Bank pipeline. Okay, so we convolve each of those templates over every frame of video, do volumetric max pooling, and so on. Okay, and we get quite poor performance. Okay, so just 2D histogram of gradients gets about 30% on the UCF 50. This is worse than STIP and so on. And if you incorporate just 2D optical flow, histogram optical flow, as well as HOG, you get good performance there. So again, motion is valuable, but perhaps in this example here, there's a better way of incorporating scene understanding into the recognition than we were able to exploit here. This is just a quick experiment we did over the last few weeks just to see what we got.
So have you used those poses to do the action? Like you showed here, they show the poses by the last pose.
Yeah.
So have you used those to do the action recognition or just the
Yeah, so here you have skeletal pose, which is just the raw pose without the histogram of oriented gradients 3D at the joint points. Bag of them, you get about 30% raw, okay, densely over the frames. And if you do use our dynamic pose, you get about 10% improvement, 40%. If you combine that with dense trajectory, you see just post hoc arithmetic mean fusion, late fusion, you get about a 3% improvement over UCF 50. Okay, so there is some complementarity there.
But I was thinking that it should help a lot because it's not really helping compared to like dense trajectory.
Right, so I think it would be helping a lot if pose was better. I think still pose is still noisy enough. And I think this is a complementary message to what Cordelia gave before. So she had perfect pose, and she showed that perfect pose was able to get, if I recall, something like 70%. I don't know what HFDB 51, some subset of HFDB 51, which is great. You know, we're given state of the art for low-level methods is like 50%. Okay, but in here we're talking, this is not manual pose, this is automatic pose. In a similar representation on top of the pose, we're taking joint points, joint angles, and even adding plot 3 at the joint points. And we see a result like this on UCA50, which is not just
What do you mean by manual?
no, fully manual. Her work was fully manual. So that's why it works so well. So I like the message, and in some sense, this is like the first two parts of this is sort of a call to arms. Right? If we could do better scene labeling, we should be able to use it for context and actions. If we'd be able to do better pose, we should be able to use that for better actions. But I think the community is not there just yet.
What kind of discriminants use manual pose? Also use like also like rigid points, parameters. Also you have
No,
new descriptors.
for skeletal pose, it's just a raw pose, just the structure. Yes. For dynamic pose, it uses hog as well as the structure, hog 3 as well as the structure.
Maybe I think from the previous talk, you see that creating have rigid point around this post joints rather than to have
I looked at the paper. They're just using that pose result is also based on the structure. It's based on the joint angles, and it's based on frame-to-frame differencing of the pose, which we did too. So I think the dynamics of the pose is what you get in the dynamic pose here, but in this other different way is related to that.
Jason, quick question regarding the action bank 2D. Cluster?
Yes.
What were you clustering on top of?
So we basically extracted hog kernels from, I don't know what we did on all the data, or it's kind of like a random subset of the data, and then cluster on that.
But just straight gating?
Straight gating,
Okay,
yeah.
I'm just wondering if you can see more sophisticated, like, exemplars of the animal cluster. It seems like the other side is finding found success there.
Yeah, we call it better on that.
Like, we have might be better than if you're.
Yeah. This really was a result that was a few days of work. Just when we started to look at the images a little more closely. Yeah, we could have done better. Someone please do better. Because I'm not going to be working on that. I'm going to be working on what you see next, which is. So we have about 2 more minutes, right? 10 more minutes. Okay. So now the rest of the talk is more about the future. It has nothing to do with automatic anything. This is a human visual psychophysical study based on video supervoxel segmentation. So we did some work with some collaborators at Rutgers, neuroscience, about essentially are actor and action semantics retained in video supervoxel segmentation. Okay, you may have seen our results like this. So this is a typical video segmentation result that you get running streaming GBH or GPH, and I'm not going to talk about video segmentation, the details of it here. If you're interested, I'm giving a talk later today where I will talk about the details of segmentation. But this is the type of results you get. I mean, there are lots of informative structure retained. That guy's snowboarding, we get him as one segment for a while. Over segmentation here, you still see the boundaries are being preserved pretty well, mid levels, and so on. Okay, so in the study, we were asking one primary question: do these segmentation hierarchies retain enough information for the human perceiver to discriminate actor and action semantics? So binary actor here is human or animal in the action. Action, these are 8 actions that, I don't know if all of them are in UCA50, I think they are. Climbing, crawling, eating, and so on. But these were things that both humans and animals can do. Right, so we had to a smaller data set here. Okay. The secondary questions we were interested in studying are: how does the semantic retention in the video supervoxel hierarchies vary with the density of the supervoxels? Those 3 panes, right? So fine over-segmented levels, medium, or very coarse segmentations. How is the shape of the action retained? Okay. How about the actor? Is it easier to recognize the action if it's a human versus an animal? Okay. How about the background? Is it static or a moving background? And how does that response time? How does the response time of the human vary with the action? Okay. So again, just so I can convince you that you can do this, what's the action here? Fleming. You got it. Baby crawling, right? It's not my baby.
What is trying to do?
Eating.
That you could do.
Yeah. And how does it help? Right now.
Gerbil or a mouse, right? It's a little harder for animals. So the question is, what am I trying to prove and how does it help? Right. So I think,
How does supervisors have recognition?
well, right now they don't because no one uses them. Right, so the goal here is to say that, well, is there enough structure in supervoxels that even humans, the oracle of visual understanding, can they understand what's happening? And the ultimate message will be yes. Okay, so then after this we want to see how can we use these supervoxel segmentations as a feature for video action recognition. For example, why not use dense trajectories only in certain regions of the image based on supervoxels?
We're actually thinking
Yeah. So here's proof that there's enough semantics there.
it's mostly about context, right? So you have the same structure as you objects, right?
So it could be about context, but I'm not sure that it's easy to understand the context from segmentations like this. But it's about the shape of, I think, the way the motions evolve.
But I mean, it's short that joints and movements, it's better that human can do this very limited technique. Like this.
Yes, and in this case there's more noise. So we want to see it, even with the presence of noise, can we still have that level of accuracy? Yeah.
Did you compare just having the human segmented out of the video, something like that?
Say the question again?
Did you test if you had a perfect human segmentation, how they would compare, like perfect human segmentation, how humans could classify the action versus if you just have supervoxels?
Yeah, no, we didn't do that, but that would be a good thing to study.
I just want to mention that K et al. Paper in ICCV 07, it effectively uses words from supervoxel segmentation to do action distribution. Yeah,
It's
and
early
in general, the results are not as good as the newer technique.
Right, and there's early work in like motion boundary histograms and so on. Yes. So essentially this is saying, supervoxels are in some sense easier to compute. You'll always get, you kind of get a repeatable result. But what features could we use there?
But everything is dependent on the quality that supervoxel segmentation do. That's a hard decision, and you never cover in this big understanding.
I think the advantage of this is the localization.
Yeah.
Localized action.
Right.
Maybe the recognition won't be that hard, but still.
Yeah. I think there's not much time left. I do have a lot of actual results that we got. So just to kind of give you a sense of what we did. We built a data set that had roughly 4-second videos that spanned the two actions, both static and moving backgrounds, the two actors, static and moving backgrounds, the 8 actions. We sampled 3 levels of granularity in the segmentation hierarchy, so a fine level, a mid-level, and a coarse level. And we were kind of, a side question for us is there a best level of the hierarchy for this? And in total, we gathered about 96. We gathered exactly 96 videos, which are 2 actors, 2 backgrounds, 8 acts, and 3 levels. And we made sure that when we were doing this study with these 20 participants, no single participant saw the same video twice. So if you either saw a fine version of one video, or the mid-level version of one video, or the coarse level version of one video. Okay, and none of these college students work in video segmentation, so they're not used to seeing these videos when they're so much harm. And one of them, who's no longer college, was my wife, and she did just as well as everyone has. Okay, so it was basically a web-based interface. You kind of saw something like this, where you load the video. They're instructed that time matters, so to hit spacebar to start the video and hit spacebar to stop the video as soon as you know. Okay, and then there's a forced choice, actor and act, or you can say you don't know. One of them that will account for that. Okay, you space it again, you see the actual video, you stop it. And just some quick results, not to go over time. We discriminate the actor quite well. Humans a little bit better than animals. I guess this might just be because we seem to observe that when humans were in the videos, they tend to be in the center of the video, whereas animals moved around a little bit more in the video. This might have been the case there. How about discriminating action? Again, pretty good, 70% overall. Okay, just for the humans. When there's dominant unidirectional motion, we have quite good performance, like walking and running. Okay.
Do they have the choice of, I mean, do they know there's no actions?
Yeah, they're taught the list of 8 actions first, but we don't give them video examples, we just use the words. Okay, so there is some semantic ambiguity, I'll give you some examples of that. Okay. So these are kind of canonical examples of running, human climbing, animal running, and so on.
So this is like a random stereogram, right? Like, down.
Random dot stereogram?
When you show humans have this capability to see 3D, and you look at just one,
Yeah.
you don't see it.
My intention is not to make a parallel to random dot stereograms. One thing we're doing now is showing videos of optical flow, showing videos of just the boundaries and not the color segmentation, just to get a better sense of what's happening. But indeed, humans can make a lot of sense of these images.
The other thing is, I mean, this kind of shows how bad with the segmentation.
How bad?
Yeah, I mean, so big. This is pretty bad for segmentation. It's not really.
Yeah, but it's good enough for humans to do action recognition.
No, it's not. Humans actually don't have to do segmentation. They can just show that video there. So the point that you are using computer vision to do something on a video and then show the humans. Actually, it's becoming worse for humans. Why would humans want to look at this kind of video compared to original video?
Well, no, I think if you think of our field as sort of a compression problem, right? Our goal is to find the smallest representation possible that can achieve the highest understanding score for whatever problem. And so the idea is not that we can show humans the whole video and they can obviously recognize what's in there, but that we're seeking representations that are efficient and also discriminative and descriptive. And this is the exploratory in that direction. Yeah, Fabio.
Did you try image segmentation? So not a product is just in seconds.
We didn't work on just frame segmentation. No.
Because the results of which image segmentation provides us with frames is slightly better than.
Yeah, it's hard to say. I mean, you've worked in segmentation, so you know if you do frame-to-frame segmentation, you'll get temporal inconsistency. Right. So my intuition says that video segmentation would do a little bit better, but maybe not that much better, just because of the inconsistency.
Humans are very good at temporal consistency, so there is often ambiguity over time. But
yeah, maybe.
Jason, did you show that?
No, we showed exactly these videos.
Okay, because it could be that the whatever causes a distraction.
Could be. Yeah, could be. There's some timing scores. The humans are better than you think. In 1 second, for most classes, they can get the right answer. We're smart.
Yes, I was wondering how to see that the human had the perceptual growth abilities.
Yeah.
So when you look at the video, even if the whole segmentation and in the common motion, this is quite a lot of the Lancaster law, allow him to group scenes together or even separate one region in the computer segment region into 2 and then grouping half to the body part, for instance.
Yeah.
So do you think that the perceptual and grouping plays an important role in this?
So I think it plays an important role when they don't know what's happening. So there'll be one chart. I'll just jump there. Let me jump there because it's an interesting chart to sort of talk about your question. I think this is the chart, right? So yes. So when they got the right answer, is the top row here. Okay, they did so in, it says here in about 3 seconds, but that's about 1.5 seconds of video. Okay, and they did. So the blue is the histogram on the right is just a kernel smoothing of the histogram, not a big deal. Right, so whether or not they were looking at an over-segmented version or a very coarse segmented version, right? They do better when they don't have to do perceptual grouping though, as much, because they're supposed to do about 77%, it's about 63%. But when they got it wrong, they just seem to look at it forever and ever and ever, as long as they could, 8 seconds, okay? And no amount of grouping can get a better answer. So in this case, I'm not sure. I guess this is telling us that maybe perceptual grouping is actually not helping that much for these videos, actually.
Or would be that technology segmentation produce the inconsistent information.
Or that.
We'll be able to group them together.
Yes. So let me just jump to the summary, and then this paper was published at a conference called International Conference on Semantic Computing. It's not in our community, but they seem to like it. In the journal version is submitted right now. We actually learned pattern classifiers on the segmentations and show that our performance with simple features like shape context is not as good as humans, but there's some promise there. I guess in summary, despite the fact that we can look at a frame of most of UCF50 and do very accurate classification, the simple things we tried with scene structure, human pose, did not yet provide enough information to leverage them. And one direction my group is working on is, can video over segmentation and video segmentation provide useful cues to help with modeling shape of action or even just context and so on. Happy to take any more questions. Code's available for most of the stuff I talked about today. If you want something that's not on the website, just send me an email. I'm happy about who has supported this work. Okay, so